Hi, my name is Megan Pierce, and I'm a senior electrical engineering major. And for my final project for ECEE 421, I did an analysis of the NE5 5234 operational amplifier. Within the amplifier, there are 5 stages that had to be analyzed: the input bias stage, the input stage, the second stage, the output stage, and the output bias stage. Each of the stages were built separately to ensure correct wiring within PSpice and to distinguish what was happening in each stage. After all the stages were built, a DC and AC analysis was done to later compare to an actual op-amp, the LM324, which was provided in the PSpice library to ensure that the amplifier I simulated was working properly and close to that of the original. In the next couple of slides, I am going to discuss key details about each stage that helped me in constructing the analysis of the NE5234. For the purpose of going over these stages, I will be referring to the transistors as Q and the number of the transistor that I am referring to. So in the input bias stage, Q49, Q60, and resistor 60 form a Weidler current mirror. Instead of dial connecting Q49, the bases of Q49 and Q60 are driven by a unity gain buffer formed by Q50 to Q53 to follow the collector of Q49. This buffer is used as a beta helper to reduce the base current error in the Q49-Q60 current mirror. To reduce the required VCC, the buffer is a complementary emitter follower, which means that it consists of a PNP emitter follower, which is Q50 and Q51, and an NPN follower, which is Q52 and Q53. Similarly, Q54 to Q57 act as a complementary follower to drive the bases of Q47 and Q58. Also, Q48 and Q59 serve as common base stages or cascodes, reducing the dependency of the currents in Q49 and Q60 on VCC. The simplified circuit shows that the core circuit is a self-biased current source using a thermal voltage. Corresponding transistors are matched except that the emitter of Q2 and is twice that of Q1. The same holds for the full bias circuit, where the emitter area of Q60 is twice that of Q49. The bias circuit produces DC voltages at 2 nodes, bias 1 and bias 5, that are used to establish scale copies of the 6 microamps current in PNP and NPN transistors in the op-amp. So in this stage, all the collector currents are equal to or around 6 microamps. In the input stage, the circuit uses a rail-to-rail folded cascode structure. Transistors 3 and 4 together can be viewed as forming one half of a differential pair, with Q5 forming the other half of this pair. This differential pair is unbalanced because Q3 and Q4 together have a larger emitter area and saturation current than Q5 by itself, causing a non-zero offset voltage. To obtain high gain in this first stage, transistors Q9, Q10, Q13, and Q14 must operate in the forward active region so that the output resistance of this stage is high. Since bias 1 is set so that the collector current of transistors 13 and 14 are equal to 6 microamps, the bias CM should be adjusted so that the collector current of transistor 9 and 10 are also equal to 6 microamps. However, if the currents in transistor 9 and 10 are simply adjusted to this constant value, the common mode output voltage at nodes 9 and 10 would be sensitive to small changes in transistors Q9, Q10, Q13, and Q14. The problem is overcome in the second stage of the amplifier, which adjusts bias CM to set the common mode output voltage of the first stage so that Q9, Q10, Q13, and Q14 operate in the forward active region. Bias 1 is affected by the bias stage, and bias CM is affected by the second stage, which I will talk about now. Nodes 9 and 10 are the outputs of the first stage and the inputs of the second stage. Capacitors C21 and C22 are used for frequency compensation, which is that they control the frequency response so that the op-amp is stable when connected in a negative feedback loop. Capacitor C22 is connected to the op-amp output, which is generated in the output stage. Combining transistor 25 and 26 to transistors 27 and 28 will form a differential pair. Since the input to this differential pair is a pure common mode signal, the collector currents of the individual transistors are approximately constant, assuming that the tail current source of Q29 has high output resistance. The diode that is used within this stage is a Schottky diode, and the voltage across it is constant. The negative feedback loop will operate on the first stage common mode output voltage, and it does not operate on the first stage differential output. The voltage that comes from node 29 to the ground is constant because transistor 25 and 26 pull up, while transistor 27 and transistor 28 pull down with equal strength. And these four transistors all are supposed to be equal to around 10 microamps. And from the list here of the transistors that helped me get the collector currents, you see that transistor 15 will have a collector current of 3 microamps, while transistor 17 and 18 will have a collector current of 21 microamps, and transistor 20 will have a collector current of 6.6 microamps. For the output stage, the transistors are not in a common collector configuration to drive its output, but it's driven by a common emitter transistor configuration, which is seen in transistor 74 and 75. Nodes 25 and 26 are the inputs of this stage and the outputs of the second stage, and capacitors 25 and 26, along with resistors 25 and 26, are for frequency compensation. The main reason to use such an output stage is so that it can drive the output node to about 0.1 volts of a low supply and about 0.1 of a high supply. In other words, this output stage is given a rail-to-rail output swing. A design goal is for Q74 to be able to push up to 10 milliamps into a load connected to the output, and similarly for Q75 to be able to pull the same current out of the load. The base emitter voltage of Q69 is equal to that of Q49, which is in the previous stage. And from the collector currents from the transistors, it is seen that transistor 64 and 63 will have collector current of 33 microamps, and 69 would have a collector current of 6 microamps. The DC currents of the other transistors in the output stage are set by the bias circuit for the output stage. The current is mirrored through transistor 32 and 33, and then also through 34 and 35, so that the collector current of transistor 35 is equal to 6.6 microamps. Within the output bias stage, there are multiple nodes that are working with the other stages previously talked about. So node P base and N base are the outputs of the output stage and inputs of this circuit. Node bias 2 is an output that becomes an input to the second stage. Node bias 3 comes from the second stage, and node bias 5 comes from the bias circuit of the input stage. And this transistor reference table was used when building the circuit so that I would know what the relative area was for each transistor being put within the op amp and be able to see what the calculated collector current would be versus the simulated collector current so that I could match the values to what I was getting on my simulation to see if my circuit was working correctly or not. So now I'm going to talk about the DC and AC analysis that I conducted for the NE5234 operational amplifier. For the input bias stage, I copied the schematic that was in the textbook for reference so that I could ensure that I was wiring everything correctly, that the nodes were placed in the right areas, and that the resistor and capacitor values were correct. When I started out, I used 5 volts for VCC and minus VCC, and when I started working, I moved on and found that I would have to use the recommended operating conditions. So for this slide, I have my input bias stage with the recommended operating condition of 2.7 volts for VCC plus and VCC minus. And on the right hand side, you can see the currents and the voltage that are going through each transistor and each node. And you can see that for majority of the transistors, 6 microamps are going through, and that helped with verifying that my bias stage was working correctly based on the transistor collector currents that were listed in the book. This is my input stage for the NE5234. And as you can see, I have my current and voltages listed after running the simulation. And when I first ran the simulation after building out each stage, I had a lot of issues in my input stage where I wasn't getting the correct current going through Q13 and Q14 of their collectors. So I had to change my V sign parameters around a little bit so that I could ensure that I was getting somewhat close to 6 microamps for Q13, Q14, Q9, and Q10. And as you can see, I got 3 microamps, which actually was able to work within my circuit when I ran it to do the DC analysis, and I was very happy with the results, so I didn't try to change anything to make it closer to 6 microamps. And my V sign parameters are 20 millivolts. My frequency is 1K. My V off is 0, and my AC is 1. And to get a gain of 50, I used my feedback resistor as 50K. My RN resistor as 1K. So for the analysis, I did a non-inverting amp and an inverting amp, and these are the 2 circuits that I used to get the data that I needed when I ran the simulation. So for my second stage, I had a lot of issues with nodes 25, 26, and 18, where the currents weren't close to what was listed in the book, and I had to tweak a lot of my output stage so that I could get my second stage to work somewhat properly. And as you can see, I got some of the numbers to be around what the textbook listed. So for Q15, I got 3 microamps, and for Q16 and 19, I got 4 microamps, and for Q17, I got 18, which is close to 21 microamps. But for Q18, I got 7 microamps coming out of the collector, which isn't close to 21, but my circuit did perform correctly, even though I did have numbers off for Q18, Q25, 26, 27, and 28, where Q27 and 28 were closer to 10 microamps than Q25 and 26 were. So for my output stage, I have my currents and voltages listed here after running the simulation, and after doing a lot of tests, I was able to get some of the current values for the collector currents for the transistors to be around what was listed in the textbook, and which also helped in my second stage and my output bias stage as well. After getting my circuits to run properly within the simulation, I was able to simulate the non-inverting amplifier using closed loop to get the voltage gain, and this is what my plot looks like after running the simulation with a feedback resistor of 50K and an input resistor of 1K to get a gain of 50. This is my plot after running the simulation for the inverting amplifier to get a gain of 50. When I simulated it and I got the signals to be plotted, I had my input signal very small, so I multiplied it by 10 so that it was visible on the plot to just have everything on one simulation plot. So this is my voltage swing after running the DC sweep simulation, and around 0.5 volts and negative 0.5 volts, my simulation will clip, and the signal will start to clip out based on the voltage swing simulation. When I did the AC analysis, I got my frequency response, which was smooth, but when I put it into dB, it gave me a little nick around 1 hertz, and I wasn't able to get it to be a smooth curve, but my negative 3 dB point is around 53.76 kilohertz for my AC analysis. After building my circuit for the simulation for the NE5234, I did a comparison to the LM324 operational amplifier, which I will discuss in the next couple of slides. So again, for the LM324 op amp, I did non-inverting and inverting amp circuits, and I simulated them to get similar results to the NE5234 simulation that I conducted prior to doing this, and these are the schematics for that circuit. This is my non-inverting amp voltage gain for the LM324, and as you can see, the simulation actually is kind of similar to what I got for the non-inverting amp voltage gain of the NE5234, which I was very happy with after doing both simulations to see that my circuit was actually working closely to the circuit given to the op amp given in the PSpice library. And this is my inverting amp voltage gain for a gain of 50 for my LM324 op amp, which was in the PSpice library, and again, it is similar to the simulation plot that I got for my NE5234 simulation. For my voltage swing for the LM324 op amp, I got a voltage swing of between negative 50 millivolts and 60 millivolts, which was off from where I got for my simulated circuit for the NE5234. So this simulation showed me that my voltage swing for that circuit was off and that I would have to do more testing to try to get the current values and the voltage values to be closer to the actual op amp so I could get a voltage swing that would be closer to this operational amplifier. This is my frequency response after doing the AC analysis for the LM324 op amp, and my negative 3 dB point was 19.56 kilohertz, around there, which was very far off from what I got for my AC analysis of the NE5234 op amp. So that showed me that after I ran all the tests before redoing the simulations over again, that something was off in my circuit, that I wasn't able to get results that was close to the LM 324 op amp. Now I will discuss what I built for the CMOS operational amplifier, which was trying to get the same response out of an op amp made of MOSFETs. So this is my amplifier design. I used a schematic out of the textbook and found that it gave me close to a gain of 50 for the simulation. And I also found that instead of using a current bias to put in a resistor value of 4K for the simulation to run, and for my VCC plus and VCC minus, I used 5 volts, and my V sign parameters were, for frequency I used 500 hertz, my V amp was 10 millivolts, my AC was 1, and my V off was 0. This is my inverting amplifier voltage gain for the CMOS design that I did in the previous slide. This is my voltage swing after doing the DC analysis for the CMOS operational amplifier design. This is my frequency response after doing an AC analysis for the CMOS operational amplifier design. And here my output bias stage is listed with my current and voltages after running the simulation. And when I first started the output bias stage, I had issues at nodes P base and N base, which then affected the output stage. But then after doing some tests and figuring out where my issues lied, which were wiring issues or node issues, I was able to get the currents to be around what was listed in the textbook after changing the area of my transistors to the correct area that was listed within the reference table.